Welcome to ePG Pathshala lecture series on data analytics. In this session on data analytics, we will be discussing about dimensionality reduction, its need and few techniques related to dimensionality reduction. So, the objective of this session are we will have to understand what is dimensionality reduction and the need for it, followed by few techniques related to dimensionality reduction. One technique is singular value decomposition. So, this session will be oriented towards learning about the steps in SVD technique. So, the session is organized as shown in the slide. We will start with what is dimensionality reduction and then understand its need. Then we will discuss about the singular value decomposition metric, and finally, we will analyze what is the complexity of singular value decomposition technique. Consider a data set shown in this slide. The data set highlights various customers along the row and their likings or ratings along the column. In case if you are going to represent this data for a year, then how many number of columns we will be having is 365 or 366 columns, and assume we are going to have some 10,000 users, then the number of rows will be 10,000. So, 10,000 multiplied by 366 is going to be a very large data, and moreover when you try to access or do analysis from such a voluminous data, more time will be spent or wasted only towards accessing the relevant data, and hence the time taken for analytics may increase. Moreover, when you try to take a look at this structure, the structure is going to be a two-dimensional view only. From this two-dimensional view, you can identify what axis is essential, and accordingly you can make use of that particular dimension or the axis alone for your analysis. Ultimately, the time taken for analysis will reduce, and this is the reason why do we require dimensionality reduction. What is the rank of a matrix? Rank of a matrix is nothing but a number of linearly independent columns for the given matrix A. For example, consider a matrix given here. The matrix dimension is 3 by 3, and hence the rank of this matrix is going to be equal to 2. Now, why we say the rank is equal to 2? Now, when you take a look at the row wise information, you will find there is no dependency between these two rows. So, we can say these two rows are not dependent, in other words they are linearly independent of each other, and therefore, the rank must be at least 2. Now, when you take a look at the third row, you will find the sum of the third and the second row generates the first row. Therefore, we can say the rank must be less than 3. So, the rank must be minimum 2 and the rank must be less than 3, hence the rank of the given matrix is equal to 2. Now, why do you require this rank? How it is related to dimensionality reduction? When we say the rank is equal to 2, we are trying to identify what are the basic components of the given matrix, and those basic components alone can be used for further analysis. So, here in this matrix, now we can represent the matrix using the two basis vectors. The first vector is the first row and the second vector is the second row. The third vector can be generated using the first and second vectors, and we can also represent the same basis vectors by means of new coordinates like 1, 0, 0, 1 and 1, 1. So, ultimately what we are trying to do is we are trying to work on reduced number of elements for the given matrix, which originally had 3 by 3 dimension. After the reduction of the dimension, we end up with 2 by 3 dimension. When we make use of the rank with respect to dimensionality, what happens is we think the dimensions, since it is large, we may not be in a position to identify all patterns related to all these dimensions. So, ultimately we may miss few of these dimensions as well as the patterns related to this dimension. So, what we are trying to do is we are trying to identify for a given data what are the dimensions that are really essential. We transform those dimensions and then use it for the purpose of visualizing the data. Having transformed these dimensions for useful analysis, then we are trying to work on a reduced set. So, take for example, here in this diagram, though the number of dimensions is going to be 3, the reduced number of dimensions which may help us in understanding or to get a great insight into the given data is going to be only 2 dimensions, that is indicated in red color. So, the number of dimensions that is essential is only 2 rather than 3. So, here rank plays a very vital role. Now, when we talk about this dimensionality reduction, ultimately what we are trying to do is, instead of working on a very large dimension, we are representing the same data set with a reduced dimension. Having represented the original data with reduced dimension, then it becomes very easy for us to visualize and get more insight into the data. But practically speaking, when you approximate it, here dimensionality reduction is actually a kind of approximation only. So, when you approximate the given data, the amount of error that may be introduced need to be reduced. So, when you are trying to work with respect to various dimensionality reduction techniques, we will have to choose that particular technique that reduces this error, the error which is introduced because of the approximation. So, why do we require reduced dimensions? So, reduced dimensions, the primary need is it discovers the hidden correlations between the topics. Say for example, you may have certain words that will co-occur, that is, that will occur together. Sometimes you may have redundant information and noisy information coming into picture. Such redundant words, or say a word which is not at all related to a given domain of analysis, will result only in an error. So, elimination of such redundant information as well as noises can be done when you do dimensionality reduction. The interpretation and visualization of your data will be very beautiful and it will be very useful when you are going for dimensionality reduction. And finally, the storage, this is what is ultimately essential when you do analysis. We should compulsorily look on the quantum of storage space that is utilized for your analysis. Once you select few of the dimensions which is relevant for your analysis, then it is necessary to hold only those dimensions and the rest of the dimensions can be ignored. Therefore, it becomes very easy for storage and the processing also becomes very easy. These are the need for dimensionality reductions. Now, let us start with an important mathematical technique called SVD, the short form for singular value decomposition. This is a matrix decomposition technique. Consider a matrix A with a dimension m by n. Now, this matrix A with this dimension will now be decomposed into 3 sub matrices U, sigma and then V transpose. Here the input matrix A whose dimension is m by n can be visualized like, say, m representing the number of documents in a given document corpus and n indicating the set of terms. So, now the given matrix may look like a document term matrix. Now, what are these sub matrices? U, let us first discuss what is U. U is a left singular vector, or we will be calculating the eigenvalues and eigenvectors for the given matrix A, and these eigenvectors will be used for the purpose of constructing the U matrix. So, it is going to be of dimension m by r, where m can be the number of documents and r can be the number of concepts. Sigma is a singular value matrix. In other words, all the eigenvalues that are sorted in descending order are placed along the diagonal of the given matrix, singular value matrix. So, you will find this matrix to be a diagonal matrix. Diagonal matrix means only the diagonal elements will be non-zero, the rest of the elements will be 0. So, this indicates the strength of the eigenvalue here, actually indicates the strength of each and every concept that is under analysis. So, its dimension is going to be r by r, which is a square matrix. V matrix is a right singular vector matrix. This right singular vector matrix is going to be a combination of n and r, where r you know is the number of concepts and n is going to be the number of terms. So, a single matrix A is decomposed into 3 matrices, sub matrices. Let us understand how these are useful for dimensionality reduction. When you take a look at this A matrix and the other sub matrices diagrammatically, how we can represent is, this U matrix is going to be the eigenvectors placed in a vertical way, and the V matrix we have the eigenvectors placed in a horizontal way. That is, in the U matrix the eigenvectors are placed along the columns, and in V matrix the eigenvectors are placed along the rows, and this singular value matrix will have only the diagonal elements having non-zero values, and the rest of the elements will be 0 values. So, ultimately it is going to be a sum of, say, sigma, which is a scalar value, multiplied by the ui vector and the dot product of ui vector and the vi vector. Once we have a matrix like this, next what you can do is, you can identify what are the rows and what are the columns that are essential, and then you can select those columns and rows alone for the purpose of further analysis. So, when you compare the previous diagram and this diagram, you may find only selective columns and selective rows are chosen, and that is going to be used for the purpose of analysis. So, the original matrix A now becomes an approximation of these selected rows and columns from the vector space. So, what are the properties of this U, V and sigma matrix? U, sigma and V are going to be unique matrices. U and V, the columns are going to be orthonormal, meaning U transpose multiplied by the original matrix U will result in an identity matrix. Therefore, the columns of these matrices are going to be orthonormal. The sigma matrix is going to be diagonal, that is, entries along the diagonal alone are going to be singular values, and these singular values are going to be positive and sorted in decreasing order. Now, let us take an example where we are modeling the users and the movies that they have watched. So, here Matrix, Alien, Serenity, etc. are the various movies. These 5 columns indicate users who normally watch sci-fi movies, that is scientific fiction movies, and the rest of the 3 users watch romantic movies. So, when you represent the users and the movies watched by these users, it is represented in the form of a matrix as shown in the slide. Now, what is that we are going to do is, we are going to take this matrix, split the matrix into U, sigma and V transpose matrix. Ultimately, after splitting into these 3 sub matrices, we are going to select only important elements and then use it for analysis. So, the original matrix A matrix has now been decomposed into 3 sub matrices, and these 3 sub matrices highlight various informations. So, this is the U matrix, this is the sigma matrix, and this is the V matrix. So, the U matrix you find the eigenvectors placed in a vertical fashion, and in the V matrix you find the eigenvectors placed in a horizontal fashion, and the sigma matrix, that is a singular value matrix, highlights the eigenvalues which is placed in a decreasing order. Now, let us understand how from a matrix A, U, sigma and then the V matrix are calculated. For that, we should have fundamental understanding of calculating eigenvalues and eigenvector. So, in the following slides we will discuss about how to derive eigenvalues, and from the derived eigenvalues how to construct the eigenvectors. Consider a matrix A with the following elements 4, 0 and 3, minus 5, have mentioned in a row major order way. Now, assume we will have to calculate A transpose, A multiplied by A transpose and A transpose into A. So, if A matrix is this, then A transpose is mere swapping of the rows into columns and the columns into row. So, we can take A into A transpose. So, A matrix and the A transpose, the resulting value will be this matrix. Then the other matrix A transpose multiplied by A. So, A transpose and the A matrix, the product of these two is these two matrices. Now, let us take a matrix and then understand how to derive eigenvalues and vector from it. Take the left matrix A into A transpose, then you subtract this A into A transpose with respect to scalar, the product between a scalar value and an identity matrix. So, I is an identity matrix. Identity matrix means a matrix which is a square matrix having only the diagonal elements with the value 1. The rest of the elements will have value 0. When you multiply a scalar value with respect to an identity matrix, you will end only with the scalar value along the diagonal element. So, the product of this matrix minus this product will provide you this value. Similarly, for the right matrix also you can calculate in the same way. Now, when you take the determinant of this matrix, it is going to be 16 minus C multiplied by 34 minus C minus 12 multiplied by 12, which is equal to 0. Similarly, for the right matrix you can calculate determinant value. Ultimately, this equation will result in a characteristic equation C square minus 50C plus 400 is equal to 0. Since this is a quadratic equation, you can have two roots. So, the two roots will be C1 and C2, which is equal to 40 and 10 respectively, and these two roots are going to be the eigenvalues for the given matrix. Now, having derived the eigenvalue for a given matrix, next what is that you should do is you should derive the eigenvectors. So, for deriving the eigenvectors, you need to first determine the eigenvector components and then divide it with respect to its vector length. Let us understand this using an example. Now, for the first eigenvalue C1 is equal to 40, let us take this matrix 25 minus 15 and 25, substitute the value of C1 in this matrix value. So, here for the C value you substitute with a value 40. Once you substitute with the value 40, the resulting matrix will be minus 15, minus 15, minus 15 and minus 15. Next, when you want to calculate the eigenvector, you will have to multiply this value with a vector. The vector dimension will be 2 by 1. So, the 2 indicates the two vector components x1 and x2. The entire product will be equal to 0 based on the characteristic equation. When you get this form, it will result in two equations and two unknowns. The two unknowns are the two components of the given vector x1. Now, with the help of these two equations, you can calculate one of the component in terms of the other component. So, when you take the first equation minus 15x1 plus minus 15x2 equal to 0, when you reorder it, that is you move x2 to the other side, minus 15x1 will be equal to 15x2. Therefore, what is x1 means? X1 will be equal to minus x2, or the other way x2 will be equal to minus x1. So, now what we can do is we can represent either x1 or x2 in terms of the other value. So, here in this example we are replacing x2 in terms of x1. So, x2 is equal to minus x1. When you substitute x2 is equal to minus x1 here, the vector becomes x1 and minus x1. When we started this slide, for constructing the vector you need to know the vector length and divide the components using the vector length. So, to calculate the vector length, you will have to take the square root of these two components. So, which is going to be x1 square plus x2 square, replace x2 in terms of x1, which is going to be minus x1. So, it will be x1 square plus x1 square 2 x1 square. So, it will be x1 square root 2. Now, use this length and divide the respective components. So, when you divide the respective components, you will get 0.7071 and minus 0.7071. So, this will be one vector, and for the other eigenvalue C2 is equal to 10, you will get another vector. Having derived the two eigenvectors, next what you can do is you can construct the V matrix. I told the V matrix is going to be the eigenvectors placed in a vertical fashion. So, place x1 as one column and x2 as another column. Now, take the transpose of this, which is going to be exchange of the row and column. So, when you take a look at this, now you will find the eigenvectors placed horizontally. Having known the eigenvalues, now you can sort them in order. So, the singular values are going to be square root of the eigenvalues. So, the first eigenvalue is 40, the second eigenvalue is 10, square root of 40 and 10 is 6.32 and 3.16 respectively. Then you can construct the sigma matrix, which is a singular value. The diagonal elements alone will have the eigenvalues in a sorted order, that is decreasing order. So, the largest eigenvalue 0.632 will be first and the next eigenvalue 3.16 will be next, the rest of the elements will be 0. So, you know V transpose and you have got S. Now, it becomes easy to compute U because you have the original matrix A. So, to calculate U, you will have to take the inverse of S matrix, that is a singular value matrix, sigma matrix, and say the transpose of V matrix, it is once again the inverse of V matrix, V transpose is once again going to be the original V matrix. So, now you can multiply A, that is the original matrix, with respect to the V matrix which you have calculated earlier in the previous slide, the V matrix, and then multiply it with the S inverse. So, the inverse of S is once again going to be the original S matrix. So, if you multiply all these three information, you will get the U value. So, now you know what is the original matrix A, what is the U matrix, the V matrix and the singular value matrix. Now, when you take a look at the U and V matrix, I told the columns are going to be orthonormal. Now, how can we understand this? Now, take the U matrix, plot the corresponding values. For example, here you have 0.4472 and 0.8944. So, take this value and plot it. Similarly, take the second column vector 0.8944 and minus 0.4472, plot a value. Similarly, for the V matrix you will have to plot. Now, when you take a look at the vectors which are placed along the column in U or in V, you can find it is going to be perpendicular to each other. So, the columns of the U and V matrix are orthonormal, in other words they are at 90 degrees with each other. So, the red color arrow indicates the left eigenvectors and the blue color points indicates the right eigenvectors. Now, if you want to know whether the sub matrices that we have calculated like the U matrix, sigma matrix or S matrix and then the V transpose matrix will result in the original matrix, means you can multiply all these three matrices, you will get a value 3.99, 2.99, minus 4.99 and 0, which is approximately equal to 4, 3, minus 5 and 0, which is the original matrix A. So, now it is obvious that given a matrix we have decomposed that and we have multiplied to get the original matrix. Having done this dimensional reduction, then where exactly the dimensions are reduced is what we need to know. I told you you are reducing the original matrix A into U, S and V transpose. From these V, S and V transpose matrix, we will have to choose only specific sub dimensions. That is, instead of choosing the original U, S and V, we will have to choose a value k such that it is very less when compared with the actual dimensions of U, S and V matrix. So, the shaded areas in this matrix are alone retained and the shaded area is represented by means of the chosen k value. Now, how do we interpret this? Say for example, if the original matrix, the movie and the user rating matrix are like this, the decomposed matrix are like this, you can identify which eigenvalue is very meager. So, from the given example we will find 1.3 an eigenvalue which is very meager, therefore, you can ignore this, meaning you are going to avoid the column that has the meager eigenvalue. When you ignore the column, similarly you will have to ignore the row. So, what happens is this 3 by 3 matrix will now get reduced to 2 by 2 matrix. Since you are ignoring a column and a row in this singular value matrix, you will also have to ignore say one column and one row in the U and V transpose matrix respectively. So, originally the matrix has 7 by 3, this matrix is 3 by 3 and this matrix is 3 by 5. Now, having reduced one of the column, now it becomes 7 by 2, this matrix becomes 2 by 2 and this matrix becomes 2 by 5. So, this is where exactly the dimensionality reduction happens, and this is what is essential for analytical purposes, because we need to identify the essential components and use it for analysis. So, here when you have this A matrix, after decomposing this into U, sigma and V transpose matrix, you will be getting an approximation. In general, this approximation will not be the original matrix A. So, now how do we understand whether a dimensionality reduction technique is working properly or not is, it is based on to what extent these approximation reduces the error. So, we will have to calculate what is the difference between matrix A, that is the original matrix, and the reduced matrix. If the difference is so large, that is the error is large, then we can conclude that dimensionality reduction technique is not working effectively. So, what is the complexity of SVD technique? So, the complexity of this singular value decomposition technique is, we are working with an m by n matrix, therefore, the order will be n by n, but we will have to consider row by row, therefore, we will have to have 2 index for the matrices. So, it is going to be n m square, or it is going to be order of n square m, whichever is going to be less, we will consider this. But when you take a look at this particular SVD technique, ultimately we are going to work on only less number of values, because you are going to choose k which will reduce the dimension of the original matrix, or sometimes you may end up with a sparse matrix, therefore, you can apply some matrix transformation techniques to avoid all those sparse values and then use it for further analysis. And you may find lots of packages that is currently available, and you can directly make use of such implementable files like MATLAB, S+, Mathematica and LinPack, wherein SVD technique is inbuilt function, you just need to call that particular function. So, to summarize, dimensionality reduction technique is very essential for any kind of data analysis, and these dimensionality reduction techniques need fundamental mathematics knowledge. In the next session, we will be discussing about few case studies related to SVD and another dimensionality reduction CUR. Thank you.